Hello, hello, hello. Am I audible? So we will start the lecture in 2 minutes. I hope I'm audible and my screen is visible. So welcome to the week 2 of this lecture session for this course Principles of Modern CDMA MIMO OFDM Wireless Communication System. So we will today solve some of the questions based on the week 1 and week 2 lecture which is taught in this course. We will start in 1 minute. Let's see if other students also join. So the first question is the bit error rate of single transmit and receive antenna. I think we can start now. 9 students has joined. Yeah. The first question is the bit error rate of single transmit and receive antenna relay fading wireless channel of average power unity given as 1, where h is the fading channel coefficient as a function of SNR, and SNR is given as power by like signal power by noise power, so P by sigma square. So for this, as derived in the lecture, like we will also derive in the live session now also, but the answer is option B, that is bit error rate is given as half. This is the approximate equation for dielectric channel SNR by 2 plus SNR. So we will see how this bit error rate we can derive. So let's suppose the received signal, let me check this video is recording or not, and the recording link will be provided in the portal, so even if anybody misses, they can watch this lecture on YouTube. So it is a single, like it is given, single transmit and receive antenna. So there will be one transmitter TX and there will be one receiver RX, and transmitter will transmit a signal and receiver will receive it. So in this, the received signal Y is given as Hx plus N. So Y is our received signal, X is our transmitted signal, and N is the noise. Okay, so what will be the received power here? So received power will come from the signal which is transmitted. So received power PR, this can be given as H square and power of the symbol P. H square is the the channel coefficient. So H is given as A e to the power of 5 as we have studied in the last lecture. So we can write the magnitude of H square will be A squared P. Okay, so this is our signal power. Now what will be our SNR? So SNR of this fading channel coefficient will be signal power by noise power. So this will be A squared P by sigma squared. Okay, and we all know that bit error rate is given as Q function of square root of SNR. Here SNR of this fading channel coefficient. So here we can also we can write as A squared and P by sigma squared. This term is general SNR, like signal is to noise ratio. So this we can write as A squared SNR. Okay. So now, so bit error rate will be Q of SNR fading is A squared P by sigma squared. It will be square root of A squared P by sigma squared. So this we can write as Q function of A, because A squared, A will come out, and a square root of P by sigma squared. So this is our SNR. Okay. Now we know what is Q of X. Q of X is integration over x to infinite 1 by square root of 2 pi e to the power of minus t square by 2 dt. Okay. So the average BER, the average bit error rate will be the integration of 0 to infinite Q of ASNR square root of SNR 2a e to the power of minus a square dA. Okay. So now here we can write SNR we can write it as mu. So this term we can write as 0 to infinite q of a, or we can take it inside a square mu 2a e to the power of minus a square dA. So now this q function we can write it as 0 to infinite q of x is x to infinite, so it will become a square root of a square mu to infinite 1 by, someone wants to join, so it will become 1 by root 2 pi e to the power of minus t square by 2 dt 2a e to the power of minus a square dA. Okay, so this is the integral with respect to t, and this is the integral with respect to a. So now what we can do, we can substitute u is equal to t by a square root of mu. So after that we will get, by integrating on both sides, du is equal to dt a square root of mu. So dt is equal to a square root of mu du. Okay, so now we will substitute this value. So bit error rate will be equal to 0 to infinite so u is equal to t by a square root of mu. So here a square root of mu is equal to t by u. Okay, and u is equal to, see, this is the value of, like, the lower limit t tends to a square root of a square mu. So now when t tends to a square mu, mu is equal to t by a square mu. So when t is a square mu, so u will be 1. Okay, so this will go from 1 to infinite, and it will become 1 by square root of 2 pi e to the power of t square. So t square will be minus a square mu by 2. So this is our u is equal to this. So t will be a square mu into u square. So there one additional term will be there, u square by 2 multiplied with dt is equal to a square root of mu du dot 2a e to the power of minus a square dA. So like this is little complex integration, like you can do by yourself. Now we will take out this constant term square root of mu, integration 0 to infinite 1 to infinite. Now 2a, there is a square because there is one a here and one a here, divided by square root of 2 pi e to the power of minus a square by 2. So it will become mu u square plus, like here we have given divided by 2, so for this minus a square it will become here 2 du dA. So now we will exchange this. First we will do with respect to dA, and then we will do integration with respect to du. So this integral will come in the second. Now this will come as first 0 to infinite 2a square root of 2 pi e to the power of minus a square by 2 2 plus mu u squared dA du. Now let's take this term as 1 by sigma square. So after that we will get 2 sigma square. So this is our, like, 1 by sigma square is given as 2 plus mu u squared. So sigma cube will be given as 1 by 2 mu u squared. So 2 plus 3 by 2. Okay, because we have taken, like, this is square root, so 1 by 2 will come, and then we are powering with 3 cube. And we also know that for a Gaussian, integral over minus infinite to plus infinite t square by square root of 2 pi sigma square e to the power of minus t square by 2 sigma square dt is given as sigma square. Okay, so this property we will use. So here we can write as this, we can write as 0 to infinite, because this is an even function. See, this is even function, ft is equal to f of minus t. So we can write as 0 to infinite 2t square square root of 2 pi sigma e to the power of minus t square by 2 sigma square dt is equal to sigma square. So now this is independent of t. So we can take it out. So we can write 2 integral 0 to infinite 2t squared by square root 2 pi this we can write as sigma cube, because this sigma will come into right hand side. Okay, and this is our first equation. Let's take this equation as the first equation. So now the bit error rate from the first equation is given as 0 to infinite 2a squared square root of 2 pi e to the power of minus a squared by 2 2 sigma squared dt. This we can write it as sigma cube here. And what is the sigma here? This sigma is 1 by 2 plus mu u square. So bit error rate is equal to 1 to infinite. So this is the one part of the integral, like from equation 1 we can write, because in equation 2 there are two integrals. The second integral we have to do now. So 1 to infinite So this is sigma cube. So sigma cube is du, and the square root of mu will come out. So here this we can write as the square root of mu 1 to infinite. Sigma cube will be 1 by 2 plus mu square to the power of 3 by 2 d u. So now we can take u is equal to square root of 2 mu tan theta, and then we can do this integral. So finally we will get this value as, like when you substitute this and do the integral, you will get, like I am not doing the complete integration, you will get something sine theta by 2, and the interval of theta is from tan inverse mu by 2 to pi by 2. So this we can write as, now sine pi by 2, that is 1, so it will become half minus sine tan inverse square root of mu by 2. Okay, and this half we can take common. So this will be our bit error rate. Also this is explained in the class. So after this, when we do the finally, like when you substitute the value of sine tan inverse mu by 2, we will get finally bit error rate as half 1 minus square root of mu by 2 plus mu, and this mu is our SNR, so we will get half 1 minus square root of SNR by 2 plus SNR. So for this question, option number B is the correct answer. So we'll move on to the next question. Like at SNR is equal to 35 dB. So SNR is given as 35 dB. Okay. So we can convert from dB to normal SNR. So 10 log 10 SNR is equal to 35. So SNR is equal to 10 to the power of, so when this 10 will come this side, so here we can write as log 10 of SNR is equal to 3.5. So SNR is equal to 10 to the power of 3.5. So deep fade occurs when the amplitude A of the Rayleigh fading channel is lower than the threshold. So deep fade occurs when A is less than square root of SNR. Okay. So is implied that A is less than 1 by square root of 10 to the power of 3.5. So probability of deep fade will be probability of A is less than square root of SNR. So this will be like 0 to, like A value will go from 0 to 1 by square root of SNR, and probability density function of A. So the probability of deep fade is nearly equal to, as derived in the lecture, 1 by SNR, and bit error rate is equal to 1 by 2 SNR. So this is directly proportional to 1 by SNR or inversely proportional to SNR. So this is equal to probability of deep fade. So when we substitute this value, so we will get probability of deep fade as 1 by SNR. So this will be 1 by square root of 1 by 10 to the power 3.5. When you substitute this value, you will get the option number C for this question. So my voice is coming. Can anyone confirm?
Yes, yes. But further in that, in last question,
Yes.
The value of A is not used. If we see 10 to power 3.5,
Yes.
From there we can calculate probability of defect.
Yes, yes.
So value of A, what you said, A is less than 1 over under root, that is not used. No?
So that is, so like this value, this is equivalent to this is the approximation. So either you can do the complete integration, but this is the approximation as taught in the classroom. So this is 1 by SNR. We'll move on to the next.
Okay. Okay, yes, yes.
So coming to the third question, that is the poor error rate of fading wireless communication channel can be intuitively explained by. So here we know that the fading event occurred in the wireless channel. So this is explained by deep fade event. Now coming to the question number 4th. The SNR required to achieve bit error rate of 5 into 10 to the power of minus 6 over a Rayleigh fading wireless channel of average gain unit is approximately. So as we have seen, the bit error rate of Rayleigh fading wireless channel is approximately equal to 1 by 2 SNR. Okay. So this approximation equation is applicable at high SNR value as taught in the lecture also. So bit error rate is equal to 1 by 2 into 5 into 10 to the power of minus 6. So this will become 10 to the power of 6 by 10. So this is 10 to the power of 5. Now when we convert this into dB, so 10 log 10, sorry, we have to find SNR. So SNR is equal to 1 by 2 into bit error rate. So this will become 1 by 2 into 5 into 10 to the power of minus 6. So this will be 10 to the power of 5. Now we will substitute this value in front of 10 log 10, then we will get the SNR value in dB. So this will be 50 log 10 base 10. So this will be 50 dB. So for this question, option A is the correct answer. Now coming to question number 5. For a given SNR, uh, power by noise ratio, the bit error rate of AWGN channel can be well approximated as. So this is taught in the lecture. Like for SNR, P by sigma squared, the bit error rate is approximated as half e to the power of minus half SNR. So option C is the correct answer. The derivation is done in the classroom. Coming to question number 6. the bit error rate of single antenna relay fading wireless channel of average.
Sir, question number
5.
Yeah, fine, sir. Okay, sir. Next.
So the bit error rate of a single antenna relay fading wireless channel of average power gain unity is given as, where H is the fading channel coefficient and SNR is given as 40 dB. So we have to find the bit error rate. So we know that for bit error rate the approximate value is 1 by 2 SNR or high value of SNR. So now 10 log 10 of SNR is given as 40, 10 to the power of 4. So our bit error rate will be 1 by 2 into 10 to the power of 4. So this will be 0.5 into 10 to the power of minus 4. It will be 0.00005. So there will be 4 0 and 5. So option C is the correct answer for this question. Now in single output wireless channel with channel coefficient H and A is equal to mod of H. So deep fade occurs when A is less than 1 by square root of SNR. So this is the condition for deep fade to occur. So option B is the correct answer for this question. Now coming to question number 8. For a given SNR is equal to power by noise ratio, the bit error rate of AWGN channel is given as. So basically the bit error rate is Q function of square root of SNR. And what is this? That is Q of square root of P by sigma square. So option A is the correct answer. And we know that Q of X is given as integration x to infinite 1 by square root of 2 pi e to the power of minus t square by 2 dt. So here Q of P by sigma square will be given as integration from square root of SNR to infinite 1 by root 2 pi e to the power of minus t square by 2 dt. So option A is the correct answer. Directly we write the square root of Q function of a square root of SNR. Now moving to the question number 9. The SNR required to achieve the bit error rate of 5 into 10 to the power of minus 10 over relay fading wireless channel of average gain unity is approximately. So again same formula we will use. So bit error rate is equal to 5 into 10 to the power of minus 10. So bit error rate will be 1 by 2 into SNR. So our SNR will be 1 by 2 into bit error rate. So this we can write as 1 by 2 into 5 into 10 to the power of minus 10. So now SNR will be 10 to the power of 9. So we can convert it into dB. So SNR in dB can be written as 10 log 10 into SNR. So SNR is a 10 to the power of 9. It will be 90 dB. So option C is the correct answer for this question. Now moving on to the 10th question. The bit error rate of a single antenna relay fading wireless channel. Again now here SNR is given as 30 dB. We have to find bit error rate. So again same formula we will use. bit error rate is equal to 1 by 2 of SNR. Okay, so 10 log 10 SNR is 30 dB. So SNR is equal to 10 to the power of 3. So bit error rate is equal to 1 by 2 into 10 to the power of 3. So this will become 0.5 into 10 to the power of minus 3. So option C is the correct answer for this question. Okay. So basically we will see some of the important formulas which can be used to solve the questions of this week assignments. So the first one is
in the last it is D, I think. 0.5 into 10 to the power minus 3 means
so it will be 0.0005. So it will be option C. Now the average, like some of the important formula I will write, so that will be useful to solve this equation, to solve this assignments. So average bit error rate for BPSK in relay fading wireless channel is given as bit error rate is equal to 1 by 2 1 minus SNR by square root of SNR by 2 plus SNR. So this is one of the important formula. Second, the condition for deep fade.
Sir, if this is only specific to BPSK, now if we change the modulation, then this will change another.
Yes, it will change. We can see for other modulation scheme also, maybe in today's lecture. Next, the condition for deep fade. When A is less than square root of SNR. Second, approximate equation of bit error rate. So bit error rate is given as 1 by 2 of SNR and quantity of deep fade is given as 1 by SNR. So we will see like to derive the bit error rate of BPSK in a different way, not in how it is taught in the lecture. So first we will see bit error rate of BPSK in relative white Gaussian noise. So in this, so let's suppose the BPSK symbols are given as 0 or 1. So 0 represent square root of minus p and 1 represent square root of p. So the yk, the received signal, is given as xk plus nk. Okay, so this is the transmitted signal X and N is the noise. So after receiving, let's suppose when the transmitter transmit this signal Xk and Yk is received at the user end. So after receiving, the decision is made. Now how the decision will be made? So let's suppose the receiver will conclude it as 1 when the value of Yk is greater than 0, and it will conclude as 0 like the symbol 0 is transmitted when Yk is less than 0. But now when will error occur? Error will occur when the transmitted symbol and the decision made is different, like it's not same. So when Xk is equal to 1, so this means transmitted is 1 and decision made is 0. So then the error will occur. So decision made is 0, this means received is 0. So here error has occurred. In similar way, when Xk is equal to 0 and transmitted is 0 because the transmitted symbol is 0, now the decision made is 1, so received is 1. So here again error has occurred. So the error occur when Xk is not equal to, the transmitted symbol is not equal to what is decision made by the receiver. So let's suppose Yk is equal to Xk plus Nk and Xk is square root of minus P because bit 0 is, let's suppose, transmitted. And for error to occur, if Xdk, like decision made is 1, so this means square root of P is greater than 0. So Yk is greater than 0. So error is occurring when square root of minus P plus Nk is greater than 0. The noise power is greater than the transmitted symbol power. In that case, error will occur. So now the probability of noise to be greater than square root of P is given as, we know that the noise is the Gaussian noise. So the probability density function is square root of 1 by 2 pi sigma squared. This is constant, so we'll take out of the integration, and it should be greater than square root of P by sigma squared to infinite, and e to the power of minus, sorry, it will be minus only root P, e to the power of minus t squared by 2 sigma squared dt. Okay, so now let's suppose this term, like t square by sigma square. So t by sigma we will take it as a u. So we will get as du is equal to dt by sigma. This implies that dt is equal to sigma du. So now let's substitute this value. So we will get the probability of error is equal to 1 by square root of 2 pi sigma square. Now t is, when t is square root of p, u will be square root of p by sigma. So because here you substitute in this, if t is equal to square root of p, so u is equal to square root of p by sigma. Okay, So the integration limit will be from p by sigma to infinite e to the power of t by sigma is u, so it will be minus u square by 2 du, and this we can write it as square root of p by sigma square. So now this function and dt is equal to, sorry here, dt is equal to sigma du. So now this sigma and this sigma will get cancelled. So this will become a square root of 1 by 2 pi. So this is our q of square root of p by sigma square. So that's why the probability of error like is equal to q of p by sigma square. So this is equal to q of square root of SNR. Now for the approximate equation, like q of x is always less than half e to the power of minus x squared by 2. So this is just for approximation. We can write it as it is equivalent to half e to the power of minus x squared by 2 when the SNR is large. So q of square root of SNR is equal to half e to the power of, where x is square root of SNR. So x squared will be minus of SNR by 2. So this will be our bit error rate for the BPSK. So now we'll take one question. What is the bit error rate of BPSK communication over an additive wise Gaussian noise channel at SNR dB is equal to 10 dB? So we can solve this in different way, whatever formula we have studied. But here bit error rate of q of square root of SNR we can use simply, and SNR in dB is given as 10 dB. So our SNR value is equal to 10 to the power of 1. So bit error rate is q of square root of SNR. So this will be q of root 10. So this is approximately is equal to 7.82 into 10 to the power of minus 4, or also we can use this equation to find. So half e to the power of minus SNR by 2, that also we can find. So the value will be approximately equal. So now we will see bit error rate and symbol error rate for QPSK.
Sir, is there any generalized formula like QPSK, then we can 16 times a scale like that?
Yes, the generalized formula is based on the constellation diagram, like the distance between the two symbols. So that also we will see.
Sir, that expression can you give, sir?
Yes, I will give. So first let me teach this, then after that I will show you the constellation diagram, and then we will see how to find the distance, and then we will see accordingly in today's lecture. So first we will see the bit error rate and symbol error rate for QPSK in AWGN. So let's suppose, like in BPSK, what happens? The transmitted symbols are symbol 0 and 1. Okay. 0 or 1. So this is like first symbol, and the second symbol is this. Now we will see in QPSK. So the transmitted symbol is equal to 0, 0, 0, 1, 1, 0 and 1, 1. So there are 4 symbols here. So now there is 4 symbols. So there will be, like, each symbols are represented using 2 bits. Like here you can see there each symbol is represented using 2 bits. Okay. So now let's suppose the transmitted bit are 0, 0, and received is 1, 1. So number of bits will be, error is 2. Okay. So number of bit error is 2 here, but number of symbol error is only 1. So here number of bits in error. So understood, like the difference between bit error rate and symbol error rate is equal to 2, and number of symbol error is equal to 1. So now we will see the constellation diagram of this BPSK and QPSK. So for BPSK, the constellation diagram is square root of P here and square root of minus P here. So this is the constellation diagram of BPSK. Now for QPSK, like there are 4 symbols, and this is the real and this is the imaginary. So we can represent as first symbol as square root of P by 2 plus J square root of P by 2. The second as in the, actually this is basically given as plus minus square root of P by 2 plus minus J square root of P by 2. So you will get in each quadrant, and each symbol is shifted by 90 degree. In BPSK, symbol is shifted by 180 degree. So this will be the second symbol. This is the third symbol, and this is the fourth symbol. this will become plus 1. So symbols are given and in this fashion. So we will see the bit error rate based on the distance also, but before that we will see total power of symbol. So total power of symbol 1 is equal to square root of p by 2 square plus square root of p by 2 square. It will be equal to p by 2 plus p by 2 is equal to p. Okay, and the noise power, is given as sigma square. So and also like as in the symbol there is two phase, there is in phase and quarter phase component in this. So this is the in phase component and this is the quarter phase component. So again the power of noise will be also divided into two phase, that is the in phase will be sigma square by 2 and the quadrature phase will be again sigma square by 2. So when you add it up you will get sigma square. So our SNR is given as P by sigma square. So bit error rate of each channel of QPSK is similar to BPSK. So that is bit error rate of QPSK of for each channel is equal to Q of square root of SNR. So both are same, but the symbol error rate, like here we will see first. Now probability of error is defined as probability of error of each bit. So now like probability of each bit received correctly, first like we will find it in a different like other way, reverse way. So the probability of each bit received correctly is equal to 1 minus p. So probability of both the symbols are received without error is equal to 1 minus PE, because both bits should received correctly, then only symbol will be received correctly, because there are two bits, so it will be 1 minus PE square. So the probability of symbol,
Sir, excuse me, sir, in this instead of symbol it should be bit, probability of both bit.
yes, so both, see, let's suppose if PE is the probability of error of each bit. So now the probability that each bit is received correctly is 1 minus PE. Now for each symbol to received correctly, we need to receive both the bits correctly. So for both the bit to receive correctly, probability will be 1 minus PE into 1 minus PE.
So that is why it should be here, it should be bit, not symbol.
No, it should be symbols. See, there is like two bits, 0, 0. So to receive the symbol correctly, we need to receive both the bit correctly. And to receive one bit,
Symbol is, sir, you said symbol is 0, 0 and bit is 0. Symbol is only 1 and bit is 2.
So bit is 2. See.
So here the symbol is only 1, 0, 0, na? But
So
bit is 2. So
yes,
that
yes.
is why I said ki probability of both the bits are
yes.
received.
Listen. What is happening? Let's suppose there is only one bit. To receive one bit correctly, what will be the probability to receive the one bit correctly? 1 minus PE, because PE is the error. So to receive it correctly, it will be 1 minus PE. Let's suppose there is one more bit. To receive it correctly, we need again 1 minus P. Let's suppose there is a 3 bit. So to receive it correctly, it will be 1 minus P. So if symbol is having n bit, then to receive it correctly, it will be 1 minus P to the power of n. For single bit to receive correctly, it will be 1 minus P. But here there is 2 bit in each symbol. So it will be 1 minus P to the power of n. So it will be 1 minus PE squared. Okay. So this is the probability that both the symbols are received without error. Now probability that one or both bits are received incorrectly. So symbol error rate is probability that either one bit or either both bits are received incorrectly. In this case, the symbol will received as the error. So this will become 1 minus PE squared, because this is the probability that both the bits are received correctly in the symbol. Sorry, here both the bits are received without error in a symbol. So now
this is what I understand.
The wording was incorrect, but the thing was correct. So this will be 1 minus PE squared. So it will become 1 minus 1 minus PE squared plus 2 PE. So this will become 2 PE minus PE squared. So we know if the probability of error is very less, let's suppose 0.001. So in that case, probability of E is much greater than probability of E squared. So here we will neglect this term for a small probability of error. So this will be equivalent to 2 into PE. So the symbol error rate is equal to 2 into PE. So in the QPSK, the symbol error rate is twice the bit error rate in this case. Now coming with respect to the this was the one equation for finding bit error rate. The second is based on the distance. So now for any constellation diagram, we will find the d mean. Like here the d mean is this. So for BPSK, d mean is how much? 2 into root p. Okay. For this how much? It will be 2 into root p by 2. So generally the probability of bit error rate is given as q of a square root of d mean squared by 2 n naught. So here for BPSK it will be q of, so d mean is 2 into root p. So it is equal to 2 into root p squared divided by 2 n naught. So this we will get as 4 p by 2 n naught. I think there is 2 is not here. Maybe I am a little confused with this formula, but it is directly d mean squared by, so it will be 2 square root of p squared. So it will be root es. But basically you remember this like it is just the probability is q of d mean square. So it is the function is based on the square of the d mean. So if d mean is more, then the bit error rate will be higher. So if distance between the two constellation is increases, q function is like this. So if d mean is increases, then bit error rate will decrease. Why? Because when we are like taking the q function, so q of x is from x to infinite. So if then this is the curve hour, so if this x value is increasing, then the error will decrease. Okay, so if d mean increases, then probability of error is decreases. Okay, so this you remember. And so this is with respect to the distance between two constellations.
So in that QPSK and BPSK, QPSK the distance is less, no sir?
QPSK distance is 2 root
less.
So it will become root p by, so this will become 4 by 2. So it will become a square root of 2p. So this is 1.4. Yes. So in QPSK distance is less. So the error will be more. The bit error rate will be more here. Symbol error rate will be same, but the bit error rate will be more because of number of bits are more here. So today we will end up the lecture here only, and tomorrow we will see more about the constellation diagram, and like I will go through the exact formula, and then we will see this in more details.
So tomorrow, next Saturday?
Next Saturday.
Okay.
So thank you everyone for attending today's lecture. So we'll close the lecture here only. We'll meet next Saturday.